Hi, before we talk about this worksheet, we need to make sure we understand this electromagnetic radiation spectrum, also called light, right? All these things are light. The energy is given off with packets of light called photons, and since they're all light, they all move at the speed of light. So notice what we have here is wavelengths here in meters, and below here we have frequency in hertz, and hertz is 1/seconds. So I also have added this wave so you can kind of see how this works. Our highest energy is over on this side, and you can see these waves, like if you were in Lake Michigan and they were coming at you really fast, they would have a lot of energy. They'd be coming at you more frequently, so they have a high frequency, and in between, crest to crest, would be the wavelength. So high energy has a short wavelength. Low energy has a low frequency and a long wavelength. So make sure you understand that. So we are going to start out this worksheet right here, and we want to express things from nanometers to meters. That is because our wavelengths are in meters, but we want an exact color, we need nanometers, okay? If we want to figure out energy, we would use this formula up here, and Planck's constant is joules per second, so our energy needs to be in joules, and our c, which is the speed of light, is meters per second. So if we use these formulas with c, they need to be in meters. So we need to go back and forth between meters and nanometers. So we have 480 nanometers. I don't want nanometers, I put it on the bottom. And I want meters, so my nanometers get crossed out. 1 nanometer is 1 times 10 to the negative 9th meters. And when I put it in my calculator, I get 4.8 times 10 to the negative 7th meters, and that's just a straight conversion. What are photons? Photons are packets of light energy. Okay, so if they're light, that means they move at the speed of light, and the speed of light is right here, 3 times 10 to the 8th meters per second. So let's look at the electromagnetic radiation spectrum, which I have another copy down here that's easier to see. If I have an increasing wave energy, I'm going this way. What happens to the frequency as I increase my energy? Well, the waves become more frequent, or they have a higher frequency. How many waves per second are hitting a spot? Okay, what happens to the wavelength is the energy's increasing, my wavelength is getting shorter and shorter. So on the model below, we are going to look at our energy drops, and the first thing to think about is where energy level 7 is, because we have a 7 to 5. Notice my energy levels, as they go up in energy, the levels get closer and closer, so my 7 would be really close to that 6. It would be about there. And then I like you to look at this and think about it instead of actually calculating it. So let's draw our arrows. 7 to 5 is about there. 6 to 4 is 6 to about 4 right there. And then we have 5 to 3, that would be that line. And then if I draw 4 to 2, I'm drawing it right here. And then 3 all the way down to 1. So which drop is going to give you the most energy? Well, here we have our electrovolts in energy, and you can see if I'm really close, 14.2 minus 14.1 is only 1 electrovolt. But down here where they get farther apart, 11.2 minus 1 gives me 10.2 electrovolts. This is a much bigger gap, so it is more energy. Okay, so which releases the greatest energy? This bigger drop. Which releases the electromagnetic radiation with the greatest frequency? Now if we go back here and look at our waves, our high energy is here and our low energy is here. So high energy produces the greatest frequency. Low energy produces the lowest frequency. So which produces the greatest frequency? The one with the highest energy, so that's E. Which transition has the shortest wavelength? Low energy has a long wavelength, high energy has a short wavelength, so it's E again, has the shortest wavelength. Okay, so I flip over my worksheet, and we are going to express blue light in meters, so we just do that conversion, and I get 4.3 times 10 to the negative 7th And then we need to calculate the energy. And so my energy is the formula energy equals Planck's constant times the speed of light divided by wavelength. And we just converted our wavelength into meters, so all I have to do is plug it in the formula with the meters. Okay? And so I want to put this in my calculator with you because we still have some calculator issues. So let's clear that. 6.626 exponent negative 34 times the speed of light, which is 3 exponent to the 8th, and I'm going to hit equals, and then I'm going to divide by 4.3 exponent negative 7. And I am going to get 4.6 times 10 to the negative 19th. My given only had 2 sig figs, so I am going to have 2 sig figs in my answer there. Okay? And then part C says to calculate the energy for 1 mole of photons. This is the energy for 1 single photon. So my energy for 1 mole of photons, here I have my energy in joules per 1 photon, and I'm going to multiply it by 1 photon moles of photons. So I want to get rid of photons. I put it up there and I want it in moles of photons. So for every 1 mole, I have 6.02 times 10 to the 23rd photons. My photons go away, and now I have joules per mole of photons, 2.8 times 10 to the 5th. Okay? So what is the speed of these blue-green photons? Well, as I said before, photons are a packet of light energy. It's light. So all light travels at the speed of light, which is 3 times 10 to the 8th meters per second. Same with the other photon. Although they have different frequencies and different wavelengths and different energies, their speed is the same. Okay, so I'm going to convert that wavelength to meters using my conversions, just like I have. And I get 4.861. Why? Because I have 1, 2, 3, 4 sig figs to the negative 7th meters, and I converted that too. And now they want you to find the energy of both lights, the red light and the blue light. So in both cases, I'm going to plug it into my energy formula, and I need my wavelength in meters. So here is our answer for the blue-green light, which is 4.089 times 10 to the negative 9th joules. Energy's in joules. Notice my joules are left because my seconds cross out, my meters cross out, and I'm left with joules, energy in joules. And over here for the red light, 3.029 times 10 to the negative 19th joules. Okay? Now over here, I actually did this before, and we are going to, let's get rid of that so you can't see my notes yet. We have a green and a red light, and they have different energies, and they're produced from the following transitions: 3 to 2, which is right here, and 4 to 2, which is right here. And what I do notice is my 4 to 2 is a longer drop, so I have more energy here. Okay, so now what can I put that together with? Well, I can put that together with my spectrum, and what I see here is, remember, my energy's increasing going this way, decreasing going this way. So my red has the least amount of energy, and my blue, green, do we have green? Green has more energy. Red down here at the low energy side, green has more energy. And since I determined that the 4 to 2 has the most energy, that's going to be my green. And the 3 to 2 has the lowest amount of energy between those two, so that's going to be my red. Okay. Here it says sketch the electromagnetic radiation spectrum. So they just want you to label these regions. So gamma, X-ray, ultraviolet, infrared, microwave, and radio, and then label high energy, high frequency, short wavelength, low energy, low frequency, long wavelength. So that's what they want you to do there. And now here is IU's favorite question. How much energy is released when an electron relaxes from 5 to 2. Well, here's my energy in electrovolts, so if I subtract them, I get how much energy was released, and that's 2.9 electrovolts. But my energy must be in joules. Okay, so I'm going to convert electrovolts to joules, and they give me this conversion information right here. So 2.9 times 1.602 times 10 to the negative 19 joules per electrovolt gives me 4.6 times 10 to the negative 19th joules. So now I have my energy in joules. They want to know the wavelength. So I know energy and I know wavelength. So this is the formula I'm going to use, but I have to rearrange it, so I'm solving for wavelength. So here it is rearranged. I plug in my Planck's constant, my speed of light. I divide by the energy I got in joules, and I get a wavelength of 4.32 times 10 to the negative 7th meters. Now the last thing we need to do is the color of this emission. When we're looking at color, instead of being in these meters, it's a breakout into more information, and they give you those numbers in nanometers. So I need to convert my meters back to nanometers, and I do that by getting rid of meters and going to nanometers. 1 nanometer is 1 times 10 to the negative 9th meters. I get 430 nanometers. So I look up here, 430 is in the violet blue area. So that's the color of that emission. Something to note is I've rounded at every step, but this is really one big problem. So normally we would round for our sig figs at the very end, and you actually would end up with that same answer. And that's how you do it.